Thank you. I'm very glad to be here. I'd like to thank all the organizers. The general theme here is to find equivalent characterizations of large cardinal notions, in this case, in terms of logic, in terms of, it turns out, certain fragments of second-order infinitary logic. So not the most natural thing you could hope for, but fairly natural under the circumstances. And we'll get characterizations of strong cardinals this way, and also Shelah cardinals, the latter being joint work with Jonathan Osinski. Let me start by way of motivation by mentioning the following theorem of Magador. A cardinal kappa being supercompact is equivalent to the Löwenheim-Skolem Tarski property for second-order logic, L2 kappa omega, the kappa meaning conjunctions and disjunctions of length less than kappa are allowed, and this property says that if a sentence of that logic has a model, then that model has a submodel of size less than kappa. And there are also characterizations like of Vopenka's principle, but in terms of logic. But I want to go downward in the large cardinal hierarchy and ask, for example, what about weaker large cardinals like strong cardinals? Or more generally, one might look at cardinals that can be defined, characterized in terms of extenders, and see if we can relate that to logic. And let's see, maybe I should have reminded, well, maybe everyone knows the definition of strong cardinal, but I'll remind the definition of strong and of Shelah cardinal when that comes up. So kappa strong means that for all lambda greater than kappa, there's an elementary embedding. J from B to a transitive model M with critical point kappa. Kappa maps above lambda, and the lambda is contained in the codomain M. And so if kappa is a strong cardinal, then we have the Löwenheim-Skolem without the T, Tarski property, which just says that if a sentence of this same logic as above has a model, then it has a model, not necessarily a submodel, it just has some model of size less than kappa. So the existence of a model reflects below the cardinal in question. This is, of course, not a characterization of strong cardinals, though, because it follows just from this B kappa being sigma 2 elementary in B, right? So this has no large cardinal strength. And kind of part of the problem is that this logic is small. So the sentences have size less than kappa. And so we're going to have to consider, if we want a characterization of strong cardinals, some kind of stronger logic. And so instead of L2 kappa omega, you could consider like L2 infinity omega, or infinity infinity. That is, you could allow infinitary conjunctions and disjunctions of any length, but then you can see easily that the Löwenheim-Skolem property cannot hold for that logic at any cardinal. It's strong enough that it can just describe any ordinal up to isomorphism. So for example, you have a just the ordinal kappa itself satisfies a sentence that doesn't reflect below kappa. You could also, another way to do it would be, if you're allowed infinitary quantifiers, also simply say there exists kappa many objects and they are all different from one another. And so you get something that obviously doesn't reflect below kappa. And so that seems to be a problem. But the way to get around this problem, that is, if we want something that is equivalent to strong cardinals, is that we can consider logic fragments of infinitary second order logic that are not closed under negation. So it makes it a little bit less natural, but by what I was saying on the previous slide, you kind of have to do something like that if you want to get anywhere, if you want to avoid triviality. And so the main logic well, there's actually two logic fragments that I'll consider in this talk, namely this one here and its dual. And I'm never entirely happy with this notation that I just made up here, but this denotes the fragment of second-order infinitary logic, which is obtained from atomic sentences and their negations by the following. So it's kind of asymmetric. You can have infinitary universal quantifiers of arbitrary length. You can say there exists x, where x is an arbitrary set of variables, and then finitary or just ordinary existential quantifiers on the other hand. And you can have infinitary disjunctions of arbitrary length, but the conjunctions have to be less than kappa. And that's what the kappa here means. And so we can then obtain the following characterization of strong cardinals in terms of this. Cardinal is strong if the Löwenheim-Skolem property for this logic fragment holds at kappa, meaning that if a sentence of it has a model, then it has a model. There just exists some model, not necessarily a submodel, or that would be too strong, but just has a model of size less than kappa. So the existence of models of these sentences reflects below kappa. Yes? That is an interesting question. If you allow only finitary universal quantifiers, then you get a virtual strong cardinal. I should mention, let's see, you could also, if we tweak this a little bit and allowed existential quantifiers of length less than kappa instead of finitary, then the theorem would also hold. So there's more than one way to do it, but this is kind of the most convenient for the purposes of this talk. And so there's a similar result for measurable cardinals, which is, I don't know, maybe it's not quite as interesting, but I'll mention it anyway, that measurability of a cardinal is equivalent to the weak Löwenheim-Skolem property for the same fragment of logic. And the weak here means that if a sentence has a model of size exactly kappa, then it has a smaller model. And in this case, we can require the smaller model to be a submodel. In fact, if you just assume that the universe of your model is the ordinal kappa, then you can get a submodel, which is just some ordinal alpha less than kappa. And the difference here from strong is the weak, which means that we're only reflecting models of size exactly kappa to begin with. And maybe this is not terribly surprising because measurable cardinals have many different characterizations known, and the ones I mentioned above aren't particularly elegant among all of those. But I think that it is interesting that we can get, in terms of, it's actually going to be the dual of this logic fragment, a characterization of Shelah cardinals, which is maybe more surprising just because Shelah cardinals are typically considered to be among the more technical large cardinal notions, and one probably doesn't expect them to have lots of different equivalent characterizations. So to get a characterization of Shelah cardinals, though, it's a bit different, corresponding kind of to the fact that in the definition of strong cardinal, you kind of naturally have an elementary embedding that allows you to reflect things below kappa, its critical point, whereas the definition of Shelah cardinal, which maybe I should write, is a more upward kind of thing. So kappa Shelah says that for every function from kappa to kappa, there is an elementary embedding. J will always be an elementary embedding in this talk from V to a model M, whose critical point is that cardinal, and how good is the model M here? Well, it contains the rank initial segment B, J, F, kappa. And so to characterize Shelah cardinals, we look at this, which is the dual of the logic fragment considered before. And so it consists of, now it's the existential quantifiers that can be arbitrary length, and the universal ones are finitary. And it's the infinitary conjunctions that are arbitrary length, and it's the disjunctions that have size less than kappa. I should mention, why is this why does this turn out to be the right logic fragment to consider? This can express the existence of a homomorphism from just an arbitrary structure that you hard code into your sentence into the structure in question, because it can say there exists a bunch of things corresponding to elements of the domain, which are then assigned interpretations that relate to each other in various ways, and then this can be used to phrase all of those conditions. So this is natural for talking about homomorphisms, and then because extenders can be defined as a kind of homomorphism, you can relate it to extenders, and you can relate it to Shelah cardinals. And so what we get is the following theorem here, and this is joint work with Jonathan Osinski, a student at University of Hamburg, and of Yuri Komsky and Benedict Löwe. And we showed that kappa Shelah, if and only if a kind of weak compactness property, which I'll call a weak compactness star, that's not a footnote, it's just a modified property slightly. So if that holds for this logic fragment, namely, if a theory consisting of such sentences above has size kappa, and every small subtheory, so every subtheory of size less than kappa has a model which is itself small, and that's the star part, so that's not part of the usual definition of weak compactness, although in the usual, and often it doesn't matter. But here we have to say every subtheory, small subtheory is a small model, then the theory itself has a model. And so this turns out to be equivalent to weak compactness. And again, the main point of this is not that one would be interested in this particular fragment of second-order infinitary logic to begin with, although, I don't know, maybe you could imagine how it would come up in some other way. But the main thing is just that there is a reasonably nice characterization of Shelah cardinals along these lines at all, which is maybe not something you'd expect if you consider this to be a large cardinal notion that's more technical than, say, super compact, extendable, whatever. Now, I want to say in the remainder of the talk, I'm mostly going to be talking about the proofs because they're not actually very difficult, especially the forward direction is very natural. So I can say just how these large cardinals give these properties, so the reflection property from a strong cardinal and the weak compactness star property from a Shelah cardinal. And in both cases, it comes from the following lemma here. And in the case of a strong cardinal, you can simply use the lemma to reflect the existence of a model below the critical point by the way that you might expect once you know that this lemma holds. So it says if you have an elementary embedding, V to M, and then you have a structure in M, that's what you want to reflect below the critical point, the existence of such a thing, and such that all relations on that structure are in M. And this is, so more or less that the power set is in M, and this is what you can get, of course, by the definition of a strong cardinal. Here you get arbitrary amount of the universe in M. And then if you have phi, which is the, which is just a sentence in the logic fragment in question, then if your model S actually satisfies phi, then M thinks that S satisfies J of phi, and then that's something which you can then reflect below using elementarity of J. But one thing that I have to point out here, which maybe looks a little bit weird at first, at least if you're not used to logics that have, well, this is a proper class size logic, right? Because you can have arbitrarily long universal quantifiers and disjunctions, and in particular, you can have arbitrarily many variables. So more than the critical point of J, for example. And so note that J actually can change phi when it's applied to it, right? Because in particular, it can make it larger, it can enlarge the set of variables, it can lengthen disjunctions and so forth. And this happens if phi is larger than the critical point of J, which can happen and which is something that we have to consider. I realize in the lemma it should say something about what kappa is. So J is supposed to be an elementary embedding with critical point kappa, and then kappa comes up again here too. So this lemma is simply exactly what we need to get this Löwenheim-Skolem property from strongness of kappa, because if kappa is strong, then for any structure S, you can get such a J here. And then from the conclusion that M thinks S satisfies J of phi and J is elementary, then some S bar satisfies phi itself where S bar is small. So exactly the kind of reflection argument reflecting something below the critical point that you would expect to do using strong cardinals. And for measurable cardinals, it still works, except that, of course, for measurable cardinals, you don't have the lambda contained in M, but what you have, well, you have all of the subsets of kappa, or all of the relations on a kappa size structure. So if you have a structure whose size is equal to kappa, then just from measurability, you get all relations on S are in M, and again, this can reflect below, but you only get the weak form, you only get reflection of if a sentence is satisfied by a structure of size exactly kappa. And so you get the weak Löwenheim-Skolem property in that case. Now, so this is not terribly surprising because this lemma is just something that one writes down in order to prove exactly these theorems. But the same lemma can also be used to prove from a Shelah cardinal the weak compactness star property holds. And so how does that work? Well, it actually uses a contrapositive of the lemma because it uses the dual logic fragment. But how does that work? Okay, so let kappa be a Shelah cardinal, and the definition there. And we want to show that this weak compactness star property holds for, this is the dual logic fragment here. And so we take a theory of size kappa in that logic fragment, and we suppose that all these small subtheories, or without loss of generality, just the ones that form T alpha consisting of the sentences up to some point alpha, we assume that each such small subtheory has a small model, and that small again is this star in what I'm calling weak compactness star. And so the main thing that I want to point out here is that it's exactly the fact that every small subtheory has a small model that gives you a function from kappa to kappa as in the definition of Shelah cardinal. So although the model S alpha is small, it doesn't have to be the same size as alpha. It could be arbitrarily large less than kappa. And so we get a function from f from kappa to kappa by just saying f of alpha is, well, approximately, it's just the size of some model, might as well be the smallest, of this small subtheory T alpha, and then we actually need a little bit more room. So we add omega to that. And anyway, the point is that we have this function which then bounds the size of the small submodels of the small subtheories of T. And then that's the function that we apply the definition of Shelah to. So we get J from V to M with critical point kappa and this much agreement of M with V. And then that's exactly what we need to use elementarity of J to get a model of the entire theory. So in M, by elementarity, first you observe not T itself, but T where you apply J to each of its sentences, which in general can stretch them out So that kind of stretched out version of T has a model now of size less than J of f of kappa. That just comes from this by elementarity. And this is in the good part of the model M. That's what we arranged here. And then that means that all the relations on the structure are in M, which, by the way, is important because we're talking about second order logic here. So we want to quantify our verb relations. We want M to be able to do that properly. And then we just apply the lemma in its contrapositive form. And so the fact that M thinks the structure satisfies each J of phi I means that the structure itself actually satisfies phi I and B. So it satisfies every sentence in the theory. And then we get the lemma for Shelah cardinal, or the theorem for Shelah cardinals. Yes? Yes. So that's what I mean by the contrapositive of the lemma is. So going back to it here, this says for the original fragment here that if a structure actually satisfies phi, then M, which is a codomain of J, thinks that it satisfies J of phi. So we're going from phi to J of phi, and then here we're going from J of phi to phi, and for the dual logic fragment. So just apply it to the negation. And so that is a pretty complete outline, or I think I can say proof actually, of the forward direction, which is what you expect to be easier, right, to go from a large cardinal to various consequences of it, in this case, weak compactness property. Now, maybe I should say something about how you prove the lemma, just real quick for completeness. It's kind of trivial, except that you need one observation, so I'm just restating the lemma here. Now, naturally, you prove it by induction on formulas, but that means that there's no induction on sentences. Obviously, you have to use induction on formulas with free variables, call it phi of x. And when you do that, you have to be a bit careful because there can be a large number of variables in such a formula. In particular, it can be larger than the critical point of J. So you've got to worry about the difference between not only phi and J of phi, but what goes on with assignments of values to the variables. And so here's, in fact, the thing that you're proving by induction is if you consider a formula in this logic fragment as before, and you consider any assignment of values to its variables in M. And S here, this is the set of all relations on the structure, so the possible values of the second order variables, and here's, of course, possible values of the first order variables. And so this is a variable assignment for the variables appearing in J of phi, if phi itself involves variables in X. And then the form of the lemma that you have to prove just involves this bit of this complication involving the variable assignment, because here we talk about phi being satisfied by a variable assignment obtained by composing f with j, whereas j of phi, we just talked about the variable assignment f, and but then once you realize that's what has to go on with the notation, then it is a straightforward induction. And so that is kind of all I needed to say about the forward direction, which is not difficult. The reverse direction involves extenders, and so I want to say a little bit about that. So to obtain a strong cardinal or a Shelah cardinal from reflection property or a weak compactness property, respectively, we use extenders and I'll start with just a very kind of easy version of the definition, which is equivalent to the more useful version of the definition. So in general, an extender is a set-sized object that corresponds to an elementary embedding from the whole universe. The following definition is not quite standard. We can talk about, for any transitive sets x and y, what I'll call an xy extender, it just maps relations on the first set to relations on the second set. How does it do that? We can talk about how an extender is derived from an elementary embedding J. So if you have an elementary embedding J from V to M, and Y is in M, and X obviously is in V, and moreover, Y is contained in J of X. So J maps X up to something that covers Y in a sense. You can derive an extender. The extender derived from J is just a function H. I'll call it H because an extender is a kind of homomorphism in this way of thinking about it. It maps the relations on X to relations on Y, and the way it does that is you got a relation A on X. You map it upward by J. Then it's a relation on J of X. And then you just restrict it to a relation on Y, and Y is contained in J of X, so you can do that. And so that's the extender derived from J. And then there's a kind of a cheapo way to define what extender means, period. An extender is just an extender that's derived from some elementary embedding, which is, of course, not, ultimately you have to get into some details and characterize that in a more concrete way. One thing I want to point out here, one way this definition is non-standard, we allow what you call a trivial extender. Trivial extender would be if J is just the identity map, and then H is simply restricting relations on a larger set X to a subset Y of X. That'll be a trivial extender. It's actually important that we allow that. You can get a surprising amount of mileage out of trivial extenders in these arguments. Although obviously you want a non-trivial one to witness large cardinals. And then the critical point of extender is just a critical point of any corresponding J, except in this case there is no critical point if it is trivial. And so we can phrase large cardinals in terms of extenders. So let me just, in the interest of time, look at a strong cardinal strong if for every lambda greater than kappa, so you want this kind of elementary embedding. What kind of extender do you need? Just an extender V kappa, V lambda, meaning it maps relations on V kappa to relations on V lambda. And measurability can be defined this way or this way. Shelah, maybe I should read that. So kappa Shelah, if and only if for every function as in the definition, there's a lambda as in the definition. And what kind of extender do you need? Again, a V kappa, V lambda extender. The trick is to guarantee this part here. So we have to say something about JF of kappa, but in terms of the extender. So we can say there's an extender H with critical point kappa, such that kappa is in the domain of H of F, which looks a little bit weird. So F is a function from kappa to kappa, so it's a binary relation on kappa. So the extender maps it up to H of F, which is a binary relation on lambda, but it's not necessarily a total function. However, if we say something approximating that totality, namely that its domain contains kappa, then in fact that is exactly what you need to characterize Shelah cardinals in terms of this type of extender. Now, to be useful, we need a more concrete definition of extender that's a kind of homomorphism, i.e. it preserves some kind of structure which you can enumerate, rather than just quantifying over J, which is a cheap way of doing it, which is that okay, you want these to correspond to elementary embedding, so just say it comes from some elementary embedding. But that's we need to define it more concretely. And so the way that you can do that, a way that you can do that, an XY extender, and here I'm lying to you a little bit, this is a footnote. This is what I'm defining here is actually a pre-extender, the difference being that it gives you a J from V to M, which is possibly ill-founded, but it can be as well-founded as you like. Well, or here it can be well-founded enough to contain Y, which is in fact, and Y, recall, could be any arbitrarily large V lambda. That's what it is when you use this, you get strong cardinals. And in fact, that's enough to get strong cardinals, is that you really just need or just V lambda is in the well-founded part of M, that M itself can be ill-founded, and that's the equivalent definition of strong cardinals almost, but not quite level by level, but it's equivalent if lambda has uncountable cofinality, which is enough for the global definition. And so, yeah. Yeah, sort of. So let's see. So homomorphism means first Boolean homomorphism. Second, you can permute the coordinates in a relation, and then this is a little bit more than that. And I tried to pick a kind of random example to be representative. The numbers 3, 1, 4, 1 can be anything here. I took them from pi. And then condition 3, this is the bounded projection operation, projection, and then by a bounded quantifier. And so this is the more concrete way to define homomorphism. And so then using this, we can say something about the reverse direction. That is, if you have first, say, the Löwenheim-Skolem property for this logic fragment, and we want to get a strong cardinal from that Löwenheim-Skolem property, how do we do that? Well, if kappa is not strong, then there's some lambda greater than kappa where you don't have this elementary embedding like this, or equivalently, you don't have a v kappa, v lambda extender or pre-extender, if you want to be precise here, with critical point kappa. And that this non-existence of an extender like this is exactly the a sense of this form that is not going to reflect. And so namely v lambda, where lambda is a counterexample of strongness. V lambda satisfies phi, where phi is a sentence in this logic fragment. And what does it say? Just colloquially, it says I, referring to itself, v lambda, should just say I am isomorphic to a rank initial segment of V. That you just need ordinary second order logic to say that. And there is no extender from v kappa to me, meaning the structure in question, meaning originally talking about v lambda, whose critical point is at least kappa. You might think you want to say critical point is exactly kappa. Critical point at least kappa means no ordinal less than kappa is moved. The little tricky point here is ultimately we'll talk about trivial extenders. Trivial extender, you could say, has critical point infinity. But originally, you can just pretend this says kappa. So this is a sentence in this logic fragment. So by the Löwenheim-Skolem property, it reflects down to it has a smaller model, a model of size less than kappa, but that's impossible. Because if this sentence phi has a model of size less than kappa, what could it look like? Well, just from the first part, the model would have to be a rank initial segment of V. So the model would have to be a rank initial segment of V. So, and it would have to be a smaller one. So it would have to be isomorphic to some V lambda bar. Lambda bar is less than kappa, but if lambda bar is less than kappa, then it's a contradiction. Because if lambda bar is less than kappa, then the second part of this, the more interesting part, fails. So phi says there is no extender from V kappa to me, but if I am now V lambda bar, then there is such an extender, namely the trivial one. So if lambda bar is less than kappa, we get an extender just by restriction. Every relation A on V kappa can be restricted to a relation on V lambda bar. And so I think it's kind of interesting how this boils down to a trivial fact about the existence of trivial extenders. Which you might not have thought was a useful concept, a trivial extender. And so that's an outline of the proof, except that I haven't really analyzed the complexity of this phi at all. And so I should probably say that to just say something about why this is the relevant logic fragment. So the complexity of phi here, here's what phi says colloquially, and why does it have this complexity? So as I said, just being isomorphic to a rank initial segment of V, of course, is ordinary second order logic that Magador may have been the first one to use that fact in the characterization of supercompact cardinals. Now, assuming that you are a rank initial segment of V, to say that there's no extender from V kappa to you or to me or to the structure in question, it looks like this. So in fact, we can put these things in front. It says that for every map that, every putative extender, it actually fails to be one. And so how do we phrase that exactly? We can use a second order variable for each relation on V kappa. These are the things that have to be reinterpreted as relations on myself in order to get an extender. And then we can use a disjunct for each instance of a relation among these relations that has to be preserved by extenders, where we think of extenders as homomorphisms. And so just to give a simple example of that, and the other ones aren't much more complicated, but you have, say, three relations on V kappa, A, B, and C. And if they stand in this Boolean relation to each other, A intersect B equals C, then what a homomorphism has to do is to assign to ABC relations on the structure in question that also satisfy this. And so we just want to say there's no coherent way of doing that for all relations on V kappa at once. So phi just says for every variable assignment, at least one condition of this homomorphism definition of extender fails. And then to control the critical point, to make the critical point exactly kappa, to get the kappa itself as a strong cardinal rather than something less, you have to do some stuff here, which in the interest of time that I'll skip. And I'll also, I'll say a little bit about measurable cardinals here. So for measurable cardinals, we're supposed to be able to get them from only the weak Löwenheim-Skolem property for this logic fragment. So it says that the existence of a model of size exactly kappa reflects. It's similar because measurability is just an instance of strongness, right? Where you can say, for example, lambda is just kappa plus 1. But you have to be a little bit careful because now what you want to do is talk about kappa, comma, kappa plus 1 extenders. In the definition that I gave, these could be two arbitrary transitive sets. So before V kappa and V lambda for strong, here kappa and kappa plus 1. The reason to do it that way is that kappa plus 1, unlike V kappa plus 1, has size exactly kappa. And that's what we need to be able to use the weak Löwenheim-Skolem property to reflect something from that model to a smaller one. And that's then really the only difference here. Otherwise, it just proceeds using the fact that measurability is an instance of strongness. I won't say anything more about that. I will say, so this bit here that I skipped over this bit about controlling the critical point. What happens if you don't do that? Then you get a slightly different result, which I think is also interesting. You can get something about the least strong cardinal, the least measurable cardinal, characterizing those in terms of the same fragment of, almost the same fragment of second order infinitary logic. Namely, the least strong cardinal is the least cardinal kappa, says Löwenheim-Skolem property holds for this. So here this kappa, what was a kappa is now omega. So the logic fragment that we're talking about doesn't depend on kappa anymore, making this a kind of natural characterization of the least strong cardinal. So in other words, the least strong cardinal is Löwenheim-Skolem number of this particular fragment of infinitary second order logic. And you can also get a similar characterization as least measurable cardinal. So it's the least cardinal such the weak Löwenheim-Skolem property holds for this logic fragment, where again we change this kappa to omega, and that's why we can only characterize the least measurable cardinal this way. This doesn't refer to kappa itself. It's just a logic fragment. The least cardinal such a weak Löwenheim-Skolem property holds for this logic fragment of that cardinal is equal to the least measurable cardinal. So the least measurable cardinal is the least cardinal at which we do not get models for any new sentences, right? So if a sentence has a model of that cardinality, then it must have already had a smaller model. It's the least cardinal at which nothing new happens for these sentences, basically. Now, let's see. So can I have like 3 more minutes, 2 more minutes? Okay. So I want to say, and this is the last slide because the following one just says that. But I'm not going there quite yet. So, because I want to say something about the proof outline for Shelah cardinals. So, we're supposing this weak compactness star property holds for now. This is the dual logic fragment. And so that says in particular, I'm just reminding you here that if a theory in that logic fragment has size kappa, and every small subtheory has a small submodel, then the whole theory has a model. And we want to show the Shelah property, so we want to show that for every function from kappa to kappa, we get such a J. And with that loss of generality, we can assume F is reasonably nice. And then, so what do we do here? Well, we want to get, in order to apply weak compactness star, we want to show that, okay, we want to come up with some theory whose small subtheories have small submodels. And the small subtheories would consist of phi i's up to a certain point, where phi I says the following, and you can easily verify that it's satisfied by this structure here. So phi I says, I am isomorphic to a rank initial segment of V, as before, now with a distinguished ordinal element, and we say something about how big it is. And that's the alpha here. So we consider structures rank initial segment of V with a distinguished element. And then phi I says there is, we're now using a positive statement here about existence of homomorphisms, and that is why it's here in this logic fragment. There is an extender from V kappa to me, and it has critical point at least kappa. You can think of it as being kappa, but it could be infinity in the trivial case. Sending F to a partial function whose domain includes that distinguished element first thought of as alpha in this model that we use to show that phi I is satisfiable. And okay, so why is phi I actually true for this structure? Well, the trivial extenders strike again. So this is just witnessed by a trivial extender. F alpha or F alpha plus 1 is less than kappa. You can just restrict, right? You can restrict every relation on V kappa to a relation on this small rank initial segment. But then by weak compactness star, you can satisfy all of the phi i's at once, and then that gives you a model S, which is actually large. So it has to look like V lambda with the distinguished ordinal alpha star. Alpha star has to be at least kappa, because in each phi I, we're saying that the distinguished ordinal is size at least I, so here alpha star has size at least kappa. And, the extender that this gives you, so the fact that all of these phi i's at once hold for V lambda with the distinguished ordinal alpha star, gives you exactly an extender of the kind that I said witnesses the Shelah property with respect to the function f. And okay, I could have explained that a little bit more thoroughly, but I better stop here. Thank you for your attention.